right, so this is where we left off the other time. We were talking about 3 identical ways of doing hypothesis tests. Okay. Now, please go ahead and do the problems. They're all pretty similar. So confidence intervals and hypothesis testing. Okay. All right, let me do this one, which is hypothesis testing about the variance, because all the other examples are about the mean. Now, for the variance is the same idea, so it's really straightforward. Now, let me show you this figure. So, yeah, this is for the confidence interval sigma square, right? But by looking at this figure, this is the acceptance region, right? So hypothesis testing is much easier. Right, here you accept H naught, and in the red areas you're gonna reject H naught. So it all comes down to really finding these 2 critical values for hypothesis testing. Right, this is 2-side, and then the same idea, if you want 1-sided, you put all the alpha probability in one side of the table. Okay, so yeah, let's do that example right here. So they give us the sample size, a x bar, but we don't need it, and s squared. Okay, and then they want to know if the true variance, which is sigma squared, okay, that's the true variance, is at least 100. Okay, so let's test that hypothesis. All right, so what we're going to use is the c-square. The c-square statistic. Remember, c-square was n minus 1, so sample size minus 1, times big S squared divided by sigma squared. Okay. So, and this is a realization, so it really should be lowercase. And I would like to put a 0 to c squared 0, let's call it. It doesn't really matter. All right, still, let me just erase that. So it should be lowercase. But anyway, right, so we have this formula, we evaluate it, right? N is 9, S squared is 90. So little less square, right? And sigma squared is 100. Now, why is it 100? Because they say it's at least 100, right? So that's we could call it mu squared naught, if you like we call the mu naught, yeah. So that's the value you want to test, okay? So yeah, call it sigma naught. Okay, and that gives you 7.2, and we compare that. Oh wait, so this is a one-sided, right? Because at least means this situation. Okay, and if you plot the chi-square distribution, which is kind of like that, right? That's your c-square. So at least is greater than, and it goes in the same way. So that would be the right tail. That's alpha, so this is chi-square of alpha. Not alpha over 2 again because it's one-sided. Okay, and this value turns out to be 15.5 from the table. Okay, so that's 15.5, and the value of c squared, we got 7.2, so we're in the acceptance region. Right, so therefore we cannot reject the hypotheses. Okay, so same idea, just different values to look up these critical values. All right, let's move on. Let's talk about pair t-test. These are really useful when we have observations that are typically from the same experiment, and you have two observations, X and Y. Okay? And then you're interested about the difference in them. Because ultimately you want to see if the random variable X is the same as the random variable Y. Okay? So what happens here is that we define capital D as the difference between the two, so X minus Y. Okay, and then we're going to assume that it's a normal distribution with mean and variance like that. Okay. Now, you could assume that safely if both X and Y are normally distributed, right? So, which is mostly the case in statistics. Okay. And then we're going to proceed exactly the same as we did before. But instead, before we called, so we replace basically X bar by D bar, and then we do everything with respect to the variable D, which before would have been the variable X by itself. Okay? So really that's one difference. Now the other difference will be how to compute the variance, okay, of the difference. So let's do an example. So here we have two columns, right? So the first column, it's the glaucoma index, I guess, from the eyes of a person. So each row would be one person and each column would be the two eyes, right? First is the eye with glaucoma and the second column is the normal eye. So you want to see if that difference, the corneal thickness, you want to see that if there's a difference between the two thicknesses of your glaucoma eye with respect to your normal eye. Okay? So that's a typical case because the measurements are taken in this case from the same person, different eyes of the same person, and you want to see if the eyes have the same thickness. Yeah. All right. So basically what we do is apply the same method we did before, but with this column, which is the difference, right? One minus the other. But the rest is the same, as you will see. All right, so we focus on this one, and then we're going to test these two, right? So the question is there a difference in the thickness, right? That's the question. So difference, you don't care whether the normal eye has greater thickness than the other or not. You just care if they're different. So the alternative is going to be mu not equal to mu naught. Now, mu naught is 0 here because, right, if mu is 0, it means that both eyes are the same. Okay. All right, so the sample mean is -4, and the sample variance or standard deviation is 10.7. And then we proceed as we did before. So everything is exactly the same as before, okay? The only difference, again, is that we performed the difference before we start anything, and it's that difference that we analyze with the method in the previous section. Okay, so here in this case, this is in the acceptance region, right, because the critical values are from -2.3 to +2.3. So that's in the acceptance region. All right, so there's no evidence of differences between the eyes. All right. Yeah. Okay, now let's do the two-sample t-test, which is a little different than the other one. Okay, in this case, we have two random samples, X and Y, with different sample sizes. Okay? So here is the case where you measure one random variable, but for two different persons, for example, or different countries, but it's the same random variable. And you want to see if they have the same mean in both countries, for example. So if you want to measure, I don't know, the height of people in different countries, so this would be x and y for two different countries, or any random variable, of course. Okay? All right, now we are going to assume that they have the same variance, because otherwise it gets a lot more complicated. Okay? So both x and y, they may or may not have the same mean. That's your null hypothesis, right? But they do have the same variance. All right. Now, in this case, it turns out that this statistic, which let's call it t, just to recycle symbols, it turns out that this statistic has the t distribution with n plus n minus 2. All right. Now, SP, we call it the pooled variance, okay, and it has this formula right here. All right, it's like a weighted average of the two independent, not independent, but the sample variance for x and for y. Okay. Now, if you analyze this formula, you would see that that would be the sample variance that you would obtain if you combine both samples, so to speak. Okay. All right. Assuming that H naught is true, by the way, right? Which is the default assumption. All right. And then it's t-distributed because we're going to have the same, right, the same ratio between standard normal and chi-square, etc. The only difference is that now the sample size, right? It's n plus n, but the degrees of freedom is not minus 1 as before, but it's minus 2. And it's because we have these two random variables, x and y. Okay, but once we construct this, we're good to go. And yeah, the steps we follow are more or less the same as before, except for a couple of things. So let's see. So this is kind of a proof of why that this approach works, right? And first of all, we notice that x bar minus y bar is normally distributed with this variance. Okay. Be nice if you were able to see why. Please try it. This is the linear combination, etc. All right, and on the other hand, we know that this is c squared, right? The statistic c squared for x, and this is c squared for y, right? So they're chi-square distributed. And then if you do the sum of both, it's also chi-square distributed, right? Because we know that the sum of chi-square distribution is chi-square with the sum of the degrees of freedom. And that's where the n plus n minus 2 appears. Okay? So, very straightforward. Then, so if you write this, then this follows. Okay, so that's kind of a proof of this. All right, so let's do an example. So here we are comparing the width of skulls from two different eras, I guess. So the modern skulls versus the ancient. Okay, so these are the numbers, the sample sizes, and you want to know if they're the same or not. So if the skulls are getting, so let's see what the question is. Yeah, so they're asking just is there a difference? So you don't care whether the modern ones are larger than the others or not. So we're going to use a two-sided test. Very good. All right, so this is the data we have for this one. So the difference in x bar minus y bar, these are the sample sizes of each. Okay? All right, and it turns out that if you apply the formula that we just saw, you would obtain 11.92. And that you have to compare with the t-value of 152 degrees of freedom. Okay? Now, we saw that the t-distribution with more than 30 or so degrees of freedom is like the normal distribution. So yeah, this should be very close to the 196 value for the normal. Anyway, so it's a lot greater than that. So we are clearly in the rejection region. So we reject H naught, that they're the same. So there is a difference, significant difference. Okay. Now it's a lot greater than this value. So this indicates that that x bar minus y bar tends to be a lot larger than 0. So meaning that the ancient skulls are a lot larger than modern ones. Okay. All right, but let's just recap this method. It's actually using a slightly different version of the t-statistic that considers these two random variables or random samples, x and y. Okay, but all the rest is identical. So we identify this guy we called t naught before, yeah, with lowercase, right? Because it's the realization of the t-value. Anyway. Okay. The last type of hypothesis testing we're going to do is known as the goodness of fit test. It is very useful in practice because it tells you whether a particular distribution fits the data well enough. Okay? So many cases you collect data, you plot your histogram, and it looks like a bell shape, but you want to know actually if it is normally distributed or exponentially distributed or whatever distribution you would like to test. Okay? So it's very useful. Okay, so in this case, the null hypothesis is that this one. Okay, so that's annoying. All right. Okay, so again, so here we're going to collect data, and then you're going to plot your histogram like that. Okay, and then these are the bins, right? Bin 1, 2, etc. That's supposed to be a 2. So bin I, right? 1, 2, I would be right here, etc. Okay, all right, and then the number that you have in each bin, not the probability, just the number. We're gonna label the observed values O. All right, so OI is going to be how many of your observations fall in bin I. Let's say that's bin I. Okay? So these are the OIs that you see here. Right? The observed numbers in bin I. Okay. So the null hypothesis, so the default hypothesis is that the probability that a random variable will fall in bin I is the same as the probability from your distribution that it will be on bin I. Okay? So that's saying that the experimental probability equals the theoretical probability, so to speak, okay? And this we're going to call the expected frequency or expected number. That's going to be your EIs. So this one, right, is just the probability according to your model that the random variable falls within each bin. Okay. Oh yeah, so that's the probability. So yeah, the actual number is the sample size times that probability. And again, this probability you calculate assuming a particular distribution f of x that you want to test. All right, and then you're going to construct this statistic Q, right? And it consists of the sum over all your bins, so the K bins, that's bin number K right here, of these differences. So the difference of the observed and expected squared divided by expected. And it turns out that this has the chi-square distribution with that many degrees of freedom. K minus 1 minus NP. NP is the number of parameters of your distribution, or to be estimated, right? So if your distribution f of x right here has two parameters, as the normal distribution has, like mu and sigma squared, then NP is 2. If you're using the Poisson distribution, only one parameter, right? Now, this result that this Q has the chi-square distribution is out of our leagues, okay? We just have to accept it for now. Yeah, it's not an easy proof, but yeah, we have to take a leap of faith here. Okay, but aside from that, the procedure is the same, right? We have a statistic, and then we have a distribution, so the recipe is going to be the same. It's going to be what is the rejection region, you know, with the critical values from the table. So the same procedure we've been looking at, just using this different statistic. All right? Okay. Now, there's a rule of thumb here that you want at least to have 5 observations in each bin, right here. Either in the OIs or the EIs. This should be just EI, not N times EI. All right, so you want at least 5 in there to have a good approximation. Okay, so let's do an example of this case. Okay, so this is a histogram. All right, so you have the bins right here, there's 0, 1, 2, and 3, and more than 6. And you have the number in each. And these are the number of bombs that fell in small areas. Okay, so you have a city, they divided it up in like a chessboard, like, and then the bombs fell, and then they counted how many fell in each square. Okay, so that's the data. So your bins are like that. Okay. So for example, 3 means that the number of squares that had 3 bombs in it are 35. Okay? Like that. Very good. And then we want to see, right? So there's a claim that the weapon, okay, so there's a plane, right? And if it's accurate, then, let me put it this way. If it's not accurate, then it's going to be like a Poisson distribution. That's the claim they're making. Right? But if it's accurate, it's not going to be Poisson. All right? So Poisson, in a sense, means that, right, remember the limit of the binomial approximation? So in each case, so in this case, all these small areas are like a Bernoulli triangle, if you will, so to speak. And if it were Poissonally distributed, all should have approximately the same number of bombs falling in. So if it's not, that's the test we're making. Let me check my time real quick. All right. Okay, so the Poisson distribution has only one parameter, right, which is the expected value. So in this case, we know that we can estimate it from the data because we know that that's true for the Poisson distribution, right, that the expected value is the parameter. So a good estimate for the parameter, it would be the mean, right, because the mean and the expected value are kind of synonyms, right? So in this case, the mean would be as follows, right? 535 divided by 576, right? Because there were 535 bombs and there's 576 areas, small squares. So that's the average number of bombs per square. So 0.929. All right, so our best model would be one with this information that the probability that you have a bomb is described by a Poisson distribution with this parameter theta. Okay, so with that, we construct the expected probabilities or expected numbers, right? So we start with the probability. So the first element here would be the probability. I'll write it right here. That's the probability. Why do I have this now? Probability, all right, x equals 0. So now, right, because 0 is the bin. I mean 0 bombs in the thing. And that's the Poisson distribution, which we know how to evaluate, right? Because we know the PMF. Remember, it's E negative theta to the x, but x is 0 now, right? So 0 divided by 0 factorial, etc. So all these numbers we're going to obtain with this formula for different values of x. Okay, so that's your probabilities. Then we multiply by 535, which is the sample size, and we're going to obtain these frequencies right here. Okay, so this row is just 535 times the probabilities we obtained before. And again, this would be the data. Now notice that we pulled some fourth and 5 and 6 bins, right? Because you don't want a 1 here. The rule of thumb is at least 5 so that you can get accurate results. Okay, so with that, we do the differences, right? You can do the differences here and then square them and then add them up. Well, divide by E first. And we would obtain 1.73. And then we proceed as we have done last couple of lectures, is compare that observed value, which should be little q naught if I want to be consistent, right, is a realization of q. And then we would compare with the critical value from the table. So the degrees of freedom is going to be k, remember, minus 1 minus np. So k is the number of bins. We have 1, 2, 3, 4, 5 bins. Minus 1 is always minus 1, and then minus the number of parameters. Now, that for the Poisson distribution is 1, just the theta that we had to compute. Okay, and again, this is less than that, so we're in the acceptance region. So we cannot reject H naught, that the Poisson model is good. Okay? So no evidence to reject the hypothesis that the Poisson distribution is a good model. Right? So there's no evidence that the flying balls could be aimed with any degree of precision. This is actually real data. So they didn't aim that well. All right, so please go through this other example. So asking the question, is it a fair dice? Okay, so this person rolled this dice 2,000 times and obtained this frequency. All right, so I guess the eyes are the dots on the dice, right? On the dice. Okay, and we want to know if this dice was actually fair or not. Okay, so yeah, please go through it. So the fair means that they're all equal to 1/6 in this case. So you have, that's your, instead of the Poisson distribution before, here we're arguing that we should use the discrete uniform distribution. Okay, and notice that we didn't have to calculate any parameter in this case because we knew already that it has to be 1/6 for all, right? So that's why in the degrees of freedom, it's k minus 1 minus 0 parameters, really, right? That's why. So that's the only difference here. All right. Yeah, and then we have this one, also very simple. So please do these, and then we'll talk in class. Very good. So that's the end of chapter 6. Congratulations again. Let's talk about linear regression now. Probably the most important application of this course. Okay, so a regression model is typically a line, like you've seen here, where you have data in the form of x, y. So the variable y is the one that we would like to predict as a function of x, and we're calling the predictors. Y is the response variable. Okay, so we would like to have a model like 7.1, right? It's a straight line, so beta naught is the intercept, right? So right over here, 0, I guess. And then beta 1 is going to be the slope of this line, right? Beta 1 right there. Oops. All right. And then we're going to assume that there's an error, epsilon. And epsilon will be IID and normally distributed like that, right? So epsilon is the error, right? So it's the difference between the observation, which are the dots, to the line. This is the regression line, okay? Yeah, I don't know why it's doing this. Okay, so that's the regression model. It's typically the regression of a line plus an error term. Now this error term, they're all IID, right? Identical, independently distributed. Normal 0 sigma squared random variable. So their mean is 0, and the variance is sigma squared. And actually, the error is the only the only stochastic term, the only random variable. And that's going to make y to be a random variable, right? Because it's going to be something plus a random variable, and that is itself a random variable. Okay, so the notation is that this regression line really gives you the expected value of y given x. And that's why we have x in lowercase, because in this whole chapter, x is not going to be a random variable. And that's a little hard to believe, right? Because up to now, x has been the random variable. But in this chapter, because these regression lines are conditionals on x, it's like x are given already. So there's no distribution. They're not random variables, is what happens, okay? So that's why always the x's in this chapter will be in lowercase. All right, so the only random variables are really epsilon and therefore y. All right. Now, this is the mental picture that we need to have, is that the regression line, right, is the same line, but given x, so for example, given x3, so we're at this line here, we're going to say that the mean of y is given right at that point of intersection, right? But then there's a distribution around y, and that's the effect of the error term, that it's normally distributed. So for each value of x, the variable y will have a mean given by the line, and then it's going to distribute according to the normal distribution with variance sigma square. Okay, so that's kind of the mental picture. These are three values of x's, and these are the three distributions for y. All right, which are always normally distributed like that, with mean given by the line, beta naught plus beta 1xi, and the variance is sigma squared. Okay, very good. So equation 7.2 is expressing the sample points xi and yi, right? So I is the index of the sample point, and n is the sample size. All right, so we said all this. Now, some terminology, the xi's are typically called explanatory variables, independent variables, predictors, or factors. So we have a lot to choose from. I typically like to use factors for some reason. Right, and the yi is the response variable or the dependent variable. Okay, and ei is the error, random variable, and then when it's realized, so when you actually collect the sample, estimate the model, and see what the errors are, we call them residuals. Okay, and this is what I was saying, that the x's are not random variables anymore. All right, so these are the assumptions of the model. Now, you can summarize it in one line like that. All right, is that these errors are all independent. That's the first little line. And they all have the same distribution, which is normal. Not only that, is that the parameters of that distribution is that the mean is 0 and the variance is sigma squared constant. Right? The sigma squared doesn't depend on x, on I, or on y, or anything. That's the assumption. Okay? So these are the three assumptions that at the end we will have to check. Right? So the strategy will be to estimate a model and then make sure these assumptions are met. All right? Very good. Now, the word linear is misleading because it turns out that the word linear refers to the parameters beta and not to x. So for example, that model, we say that it's also a linear regression model. So the word linear regression, that linear term, refers to the betas, right? Because you don't see a beta raised to the power of anything, right? So it's linear in beta. You don't see logarithm of beta, etc. Okay, so you could have any nonlinearity on the x's. You have x squared, x cubed, of course, any function. So it doesn't have to be linear in x. It's linear in the betas. Okay, so let's get that out of the way. So it's much more general than you might think, right? Okay. Now, because in general we're going to be dealing with several factors, several x variables, it's nice to work in matrix notation. Okay. All right. So the model 7.2, which was a single with a single variable x in matrix notation, would be 7.5 with these vectors. Okay. Yeah. So please go to 7.2 and well, 7.2. I think I know what it was. It's the model y I equals beta naught plus beta 1 xi plus ei. Okay? So in matrix notation, that's going to be the case if you define things like this. Now notice the first column of ones that you need in the matrix X here. And it's because you want the beta naught, right? Because you're going to multiply this by beta and then add the term. Now, the beauty of this notation is that when you have a lot more factors, right? So let's say this is, okay, GDP of a certain country, or country I, right? Let's postulate a model that the GDPs should be a function of, so the first x1 might be the population of the country, the second one might be, I don't know, the climate, the temperatures in the country, if that's a variable. So see, in general, you can have up to p variables, so no limit really on variables, right? So whenever you have more than the one variable, it's easier to work on a matrix notation, okay? And this is kind of the mental picture of all these models. So you have all these explanatory variables, right, which are potentially infinite or very large. And then you have this model, the system, I will call it model, the regression model, right? And that predicts a response. Now, notice that this is the same idea behind machine learning models that hopefully we'll have time to talk about. Right, so you have a bunch of predictors, these factors, right, features, they call it too, that are able to, or should be able to explain your observations of Y. Now in machine learning, this model is not going to be a regression, but it might be a neural network, right? But regression is a special case of those models. Okay, so this model 7.6 with a lot more variables can be expressed in the same way 7.5 before, just by defining the same for these three vectors, but X now is going to be a much larger matrix, right? Which would have, the column for the beta naught and then one for each of the factors. And we call this guy the design matrix. So let's interpret these coefficients. Okay, let's take the simple model with three factors, right? So beta naught is, of course, the intercept, and then all the others, right, you can see that they correspond to the partial derivatives. Okay, so the betas in this simple model, and we call this a main effect model. Main effect. Okay, so in a main effect model, we have this interpretation of the betas. So main effect, by the way, is just when you have a beta times a variable. Now, other models that we're going to see, you could have, for example, you could have plus, beta 4 times x1 times x2. Right, so you're combining variables. You can do that, right? And you can do whatever, like x1 divided by x2 or raised to the power of x2, whatever you want. But this no longer would be a main effect model because you have combinations of terms like that. All right, but for a main effect model, that's the interpretation, okay? So it's the marginal change. It represents the marginal change in y. Okay, and notice that it has units, right? The units would be the units of y divided by the units of xj in that case. Okay, and this is one of the first tests you should make. So you calibrate your model, you train your model, you obtain the parameters. The first thing you should check is that the sign, right, that the sign of beta makes sense, right? Because you should be able to know if that variable should induce that the variable y increases or decreases, like the GDP we're talking about. So population, the more the population is, the more the GDP should be, right? Because this is the total, economic activity. So the more people you have more economic activity. So if the beta that results from the model is not positive, then you know something's wrong, right? And that's the idea of marginal change. Okay, so this is the example of a quadratic model, right? So we have x and then x squared, right? But in matrix notation is easy, right? We just add one column per new variable, and x squared could be considered as a separate variable, okay? So for example, in this is not a main effect model, right? Because we have xi squared. So if you take derivatives here, for example, dy I dxi, so you see that's going to be beta 1 as before, but now we have the other term, so 2 beta 2 xi, right? So in this model, the betas no longer represent the marginal effect. Now it's more complicated because, it depends on the level of xi, etc. So this interpretation, again, is only valid for main effect models. Okay, and these are the interaction terms that I was talking about, right? So it's whenever you combine x1, x2, right? And again, it could be anything like log of x1 divided by, I don't know, hyperbolic tangent of x2. That wouldn't be a main effect model either. All right, so one needs to be careful there. Okay, and this is how you would construct the design matrix, right? You always start with one column of ones and then one for each variable, and then we have this third variable, right? x1, x2, and so we do the product of all these. Okay, so hopefully you get the idea now that these linear models are much more general than you could think initially. All right, and with that, I'll see you in class.